What's up, everybody? Welcome back to another video. In today's video, we're going to very briefly cover talking about tonicity and osmolarity. Okay, these are very simple concepts that people get confused very often. Okay, and they don't know how to differentiate with it. So today, we're going to talk about what tonicity is, what osmolarity is, and we're going to do a couple practice problems to really get it down pat. All right. Without further ado, let's get right into it. So when we start talking about tonicity and osmolarity, we have to get introduced into a very simple concept of solutes and solutions, okay? And believe me, we won't go into too much detail, just enough for you to understand. So let's say I have some sort of beaker or a test tube, right? And within that beaker or test tube, I have some level of solution, okay, or water or liquid, okay? Now that amount of liquid inside of that beaker is called a solution. All right. And inside of a solution are generally going to be tiny little things that are dissolved in there. Okay. Tiny molecules that are dissolved in there. These could be salts or they can be macromolecules. Okay. Doesn't really matter. But these guys that are dissolved in there are called solutes. So solutes are dissolved in a solution, okay? The easiest way I like to always think about it is with an example. So sodium, for example, which is just salt, inside of water. The water is the solution, the sodium is the solute, okay? Great. Now you know this terminology, let's introduce this other thing. Let's say I would add a membrane inside of this actual tube, okay? And this membrane is supposed to kind of represent our plasma membrane or our phospholipid bilayer, okay? Let's say I were to do that. The molecules or the solutes that can actually freely move across this membrane and back are actually denoted as penetrating solutes. Okay, so there are penetrating solutes because they can move freely back and forth from that membrane without the need of any carrier or channel. But then you have other solutes that can't penetrate it readily. So watch, this dude tried to do it, he couldn't do it. What about this guy? He's trying, he can't do it either. These guys are non-penetrating solutes, okay? Now, non-penetrating solutes. Great. Now, if you remember in my previous video talking about the cell membrane, I mentioned that you have to remember the law for osmosis is that water loves to go from an area of high concentration to an area of low concentration. That's its concentration gradient, okay? Naturally down it, just like everything else. But that's not all. Water loves to move from an area of low solute concentration to an area of high solute concentration. Okay, but this begs the question. I just said water goes from low solute to high solute, but I also just said that within a solution, there's two kinds of solutes. There is a penetrating solute and a non-penetrating solute. So are we talking about this one or this one as regard to this law? And that is a great question. And the answer to it is we're talking about non-penetrating solutes, okay? And let me tell you why. A penetrating solute, just like any other molecule that can cross the membrane freely, will reach equilibrium, okay? So let me explain this. This solute over here, right, it can go down its concentration gradient until the concentration of that solute on this side of the membrane is equal to the concentration of that solute on this side of the membrane. And at that point, there is no more net diffusion occurring, meaning that molecules are still moving in and out, but because their concentration is the same, somebody observing this would see nothing happening. Okay? So why does that matter in terms of osmosis? Well, because water loves to move from area of low solute to high solute, but if the solutes start to equilibrate such that there is no kind of difference across the membrane, then water is not going to want to move anywhere. Okay, so when we're talking about water movement, it has to be caused by non-penetrating solutes because their concentrations will always remain different on one side versus the other side of the membrane because they cannot penetrate the membrane easily. Okay, that's why we say that non-penetrating solutes are the ones that bring about something called an osmotic pressure, which is a pulling pressure. And again, we talked about this in my last video. Okay, so now that you understand this basic concept, let's go ahead and talk about the definitions of osmolarity and tonicity, okay? Alrighty. So, tonicity is defined by, or it's really the term we use to describe non-penetrating solutes, okay, in a solution. Well, what would count as a non-penetrating solute in a solution? What would count? Okay, well, an example could be sodium ions, or potassium ion, or chloride ion, okay, or glucose, or proteins, okay, if we're talking about biological systems, okay. Now, here's the thing. You should be seeing a pattern here. Anything that is either charged or water soluble is not going to be able to penetrate the membrane. We've already talked about this. This is just basic membrane physiology here. Okay? And the reason is because of the fact that they are either too large or they have a charge or what have you, or they're water soluble. And because of that, they're non-penetrating solutes. Now, non-penetrating solutes, I told you, have a very, very cool special property where they can create an osmotic pressure, which, remember, is a pulling force. Okay? Pulling force. Awesome. Now, that's what tonicity is used to describe. Tonicity is used to describe our non-penetrating solutes in a solution. Okay? But what's a term that I can use to describe penetrating solutes and non-penetrating solutes? That would be osmolarity. So osmolarity describes non-penetrating, okay, plus penetrating solutes, okay, in a solution. Great. Okay. And a common example of a penetrating solute that you'll be given on tests, for example, is going to be urea, okay, or urea, which is a nitrogenous waste product made inside of the kidneys, all right? And this urea, all right, sorry, not in the kidneys, made in the liver but excreted out in the kidneys. This urea, right, is very much so lipid soluble, thus it can easily cross the plasma membrane, hence why it's called a penetrating molecule, all right, or penetrating solute. Anything else that is lipid soluble would also count as a penetrating solute, okay? Now, osmolarity, the main difference between tonicity and osmolarity is that osmolarity is talking about both non-penetrating and penetrating, so we can't really use osmolarity to define osmosis, right? Or use it to kind of discern water movement. But tonicity, since it's only talking about non-penetrating solutes, and we know that non-penetrating solutes are the ones that are involved in the movement of water, then we can actually refer to tonicity to explain the water movement of in relation to the cell. Now, here's another important note that I should tell you, is that, and let's change color here, tonicity, okay, more often than not, anytime you see tonicity, unless explicitly told, it is explaining the environment surrounding the cell. Okay, so it's explaining the environment, not the cell. All right, and you guys know that the environment in this scenario is referring to the fluid surrounding the cell, which is the interstitial fluid. Okay, so tonicity explains the environment, not the cell. All righty. Now, speaking of the cell, what is the normal tonicity of a cell? Meaning the normal concentration of non-penetrating solutes. Well, the normal tonicity of a regular cell is around 300 milliosmoles per liter. Okay? Guys, we have to pause for a second and talk about what this unit of measurement is. milliosmoles per liter, okay, is talking about the concentration of solutes in a solution. Okay, so let's write this down here. It's talking about the concentration of solutes in solution. And when we're talking about both osmolarity and tonicity, we use milliosmoles per liter as a unit of measurement. Okay, that's exactly what it is. It's a unit of measurement. It's the exact same as saying, for example, millimoles per liter or moles per liter. Okay, now for a basic understanding of, for you to understand what a mole is, it's basically a number. Okay, so you know how sometimes we say, okay, I have a dozen eggs. What does a dozen refer to? It's referring to a number, a specific number, which is 12. Dozen eggs means I have 12 eggs. Well, a mole is kind of the same thing, but instead of the number that it's referring to being a dozen, the number that it's referring to is actually equal to 6.02 times 10 to the power of 23, okay? This is Avogadro's number, okay? That's what a mole is referring to. And it's an extremely, extremely, extremely big number because it's raised to the power of 23. All right. Now, milliosmoles, okay, is very common. Milliosmoles is referring to that concentration of solutes in a solution that contribute to the osmotic pressure, okay? So that's what osmolarity is most commonly used for. And again, we'll talk about the definition a little bit more later, okay? But I just want you to understand what moles is and why we're actually kind of using it as a unit of measurement here, okay? And by the way, osmolarity should not be confused by osmolality. Osmolality is the unit of measurement in milliosmoles per kilogram, not per liter, okay? So those are two different things. Related, but different. Okay, now let's go through a very simple example to actually show you what I mean when I say that non-penetrating solutes can affect water movement, okay? So let's say we have a red blood cell, okay? And this red blood cell right over here will be placed in 3 solutes of varying concentrations, of varying tonicities. The tonicity outside of the cell here will be 300 milliosmoles per liter. Okay, and by the way, you might see me from time to time switch between writing as milliosmole per liter or milliosmole per liter, okay? And the big M is just a short way of saying mole, okay? Anyways, the 300 milliosmoles outside of the cell in tonicity, okay? So this is tonicity. And the inside of the cell we know is 300 milliosmoles per liter normally, right? So if I could depict the concentration of the non-penetrating solutes, okay, I would do it in these little blue dots. Boom, boom, boom. All right, so there's some non-penetrating solutes, but their concentration is pretty much the same inside versus the outside. So will there be any water movement, guys? Yes or no? Okay, well, if you're saying no, then you're absolutely correct. Why are you correct? Because there's the same amount of non-penetrating solutes outside of the cell as there is inside of the cell. And how do I know this? Because inside of the cell has a tonicity of 300 milliosmoles per liter, and outside of the cell is also 300 milliosmoles right now. So inside is the same as outside, which means there's no net movement. Great. Now let's take a look at this red blood cell in this other solution where the tonicity changes to 400 milliosmoles per liter. Okay? What do you think will happen to this cell now? And you know what? Just for continuity's sake, boom, 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 boom. We're going to put a whole bunch of these dots now, these non-penetrating solutes, because the tonicity outside is much higher than what it is inside the cell. If that is the scenario, guys, look at what's going to happen. Look what's going to happen. You guys know that water likes to move from an area of low solute to high solute, okay? That is the rule. You just have to understand this rule and follow it. Low solute to high solute. Okay, What is solute referring to here? Non-penetrating solute. Okay, what is the concentration of non-penetrating solutes inside of the cell? Okay, concentration of solutes in a solution. Okay, it's 300 milliosmoles in a normal cell. Alrighty, what about outside of the cell? 400 milliosmoles per liter. Okay, so where is low solute and where's high solute? The low solute is inside of the cell, high solute is outside of the cell. So the water will go from inside of the cell to outside, okay? And it'll keep doing this until, watch what's going to happen. Until, and we can remove this guy and redraw it as this shriveled up looking red blood cell. Why is it shriveled? Why did it shrink? Because a lot of water exited out, okay? A lot of water exited out and it made the cell shrink in size, okay? Great. It's kind of like a balloon, okay? When you have this kind of balloon and you're filling it up with air, it, balloons out, okay? But then as soon as you suck the air out, all right, what happens to that balloon? The balloon starts to shrivel up, okay? That's exactly a very similar concept. Now, let's say we put our red blood cell in another solution, and this time, the non-penetrating solute concentration outside of the cell is actually very, very low. It is around 200 milliosmoles per liter. Okay. And so in this case, you can tell that the tonicity outside is much lower than the tonicity inside of the cell, which is, again, 300 milliosmoles normally. Remember that number. And if that is a scenario, the low solute concentration is outside and the high solute concentration is inside. So water will tend to move inside of the cell. And you know what's going to happen in that scenario, guys? I'll tell you what's going to happen in that scenario. We are going to swell up this red blood cell, okay? He's going to become much, much bigger. And that is because a lot of water will actually move in due to osmosis, okay? Great. Now, you have to understand how to describe the environment surrounding the cell, right? Because we said tonicity explains the environment, not the cell. So if we say the outside is 300 milliosmoles, which is the same as what's inside, right? We have to give that a kind of a name. And so we say that the outside and inside have the same amount of tonicity, and that's called isotonic. If the outside of the cell is more it has a greater tonicity than the inside of the cell, then we say the solution is hypertonic. You guys know hyper, this prefix, it means greater or larger or higher, okay? And this last one, when the tonicity of the solution is lower than the tonicity inside of the cell, we say that solution is hypotonic. Okay. Pretty easy, I think. This example proves to us how this osmosis works and how tonicity and osmolarity play together. Now, I'm going to keep playing around with this idea of tonicity before I introduce a question to you, like a word problem to you. So suppose this, okay? What is the tonicity in this example and what happens to the cell? So, seeing that this is our plasma membrane, this is the intracellular fluid, this is the extracellular fluid. The outside is 200 milliosmoles per liter in tonicity, and the inside is 500 milliosmoles per liter in tonicity. Okay? What will happen to the movement of water? Well, let's think of it like this, okay? Water likes to go where? It likes to go from an area of low salt concentration to high salt concentration. Remember, all this number is saying is the amount of salt or the amount of solute, okay? And if it's tonicity, and if you were specifically told this number is tonicity, then you know it's non-penetrating solute and you know it's talking about water movement, okay? And same thing here, okay? I told you that this was tonicity from the start as well. So, water likes to go from low salt to high salt, specifically low non-penetrating salt to high non-penetrating salt. And so the water will move this way very simply, okay? Easy peasy. Now, we can also say if the water was in a high concentration here, okay, which generally it is, okay, what would happen? The water would move into the cell. okay, down its concentration gradient, but also following its a non-penetrating solute gradient, okay? So over here, let's say I have 1, 2, 3, 4, 5 non-penetrating solutes, but over here I only have 1 and 2, okay? So which one is more? Well, 5 non-penetrating solutes, so water will move here. You can see there's two things moving water. There is the concentration gradient of water, and then there is the osmotic pressure that pulls water. All right, and the osmotic pressure is created by these non-penetrating solutes. Great. Let's take a look at this one. Let's say that the extracellular fluid osmotic concentration, or tonicity, is 500, and the tonicity inside is the regular, 300 milliosmoles per liter. What happens to the cell? Well, this should be pretty easy to you. Water likes to move from where? Low salt to high salt. Which one's higher, 500 or 300? 500. So water goes down its concentration gradient. Ooh, one thing I forgot to mention for this one, by the way. If water moves into the cell, what happens to the cell? Which is the question. The cell will swell up. Okay, and what is the tonicity? Is the environment hypotonic, isotonic? Well, it's 200 milliosmoles relative to the cell, all right? And we know that tonicity describes the environment, not the cell, so we must conclude that the solution is hypotonic. Easy. Let's move on to this one, which we said water will move from low salt to high salt. Okay, pretty easy. If that is the case and water is moving outside of the cell, what happens? Well, the cell will shrink, and because the cell is shrinking and the outside is higher in osmolarity or in tonicity, we actually say that this is hypertonic. Okay, so again, pretty simple kind of way of doing it, okay? And you know what? Even if I hadn't told you these, and I just told you that there is 4 non-penetrating solutes here, and there is 5 non-penetrating solutes here, and there is 4 water molecules here, and 3 water molecules here, okay? Which way does water go? Well, water moves down its concentration gradient, and it also goes from an area of low salt to high salt. So this one is the osmotic pressure, whereas this one is the concentration gradient, okay? This concentration gradient is kind of pushing water in this direction, while the osmotic pressure is pulling water in this direction. Okay, beautiful. Let's move on to actually calculating a question, okay? So, this question said that if a cell has an osmolarity of 300 milliosmoles per liter and is placed in a solution of 200 millimoles per liter of potassium chloride and 50 milliosmoles of urea, find the osmolarity and tonicity of the solution. And in this kind of question, when you're asked find the osmolarity and the tonicity, okay, you usually have to both calculate it and then state whether the solution is isoosmolar, hypoosmolar, hyperosmolar, isotonic, hypotonic, hypertonic, and for our purposes, also say what happens to the cell as well. Okay? All right, so let's do this example of a question, all right? The first thing I usually like to do is write down what I'm asked for, okay? So I'm asked for osmolarity, okay? And I'm asked for my tonicity. All right. Now, with the osmolarity, we know that it asks me for calculating non-penetrating and penetrating solutes. Okay, so if I want to figure out the number, I just have to plug the non-penetrating plus the penetrating values in. And I know this because of our definition right over here. Okay, so let's figure out what is the penetrating solute and the non-penetrating. Well, let's pull out the highlighter here, okay, just for the sake of easy work over here for us. So we say that we have 50 milliosmoles of urea, 20 millimoles of potassium chloride, and the cell has an osmolarity of 300 milliosmoles. Okay, so I can kind of ignore this bit of information for now, Okay, I don't really need that information right now. What I do want to know is the relative concentration of the solutes in the solution as relates to the cell. So we have 50 milliosmoles of urea, and that's our penetrating, because I told you urea is lipid soluble. So we have 50 milliosmoles per liter of urea plus. Where's the non-penetrating solute? Okay, 200 millimoles. But you know, it's actually wrong to write 200 millimoles of potassium chloride. You know why it's wrong? Because the units millimoles per liter actually measure the concentration of a compound in a solution, whereas milliosmoles measures the concentration of a solute in a solution. So you might be asking me, hey, how do I convert from millimoles to milliosmoles? Well, it's not like a conversion factor, really. If you understand how, or the number of particles a substance dissociates into, you can convert from millimoles to milliosmoles. And that just literally requires you to understand what the substance is made up of. So potassium chloride, what is it made up of? It's made out of potassium and chloride. And when I place it into a solution, it immediately dissociates into a potassium ion and a chloride anion. Okay, so potassium cation and a chloride anion. These are the constituents. Now, notice how I have one solute now and the second solute. Each of these solutes will exert an osmotic pressure, okay? So this one will have a pulling pressure and this one will have a pulling pressure. Thus, when I'm calculating osmolarity, I actually have to take into account both of their pressures. So what do? I take their concentration, 200 millimoles per liter, and I multiply it by 2, which gets me 400 milliosmol per liter of potassium chloride. That means that my osmolarity is 450 milliosmoles per liter. Okay. And that should be milliosmoles per liter. Great. All right. Now, we know what our osmolarity is. Now let's calculate our tonicity. What is the definition that we said for tonicity? We said that it's only our non-penetrating solutes, which means that it's going to be 400 milliosmoles per liter, right? Why is it only 400 and not 450? Because tonicity takes into account only the non-penetrating solute, which is our potassium chloride and not urea. Okay, that's great. That's great. Now, we know that the cell has an osmolarity of 300 milliosmoles. Okay? What is the words that we can use to describe the environment as it relates to the cell? Okay? Well, we know that the outside is 400 milliosmoles per liter, okay? And we know that inside of the cell is normally about 300 in tonicity. So, we can say that the outside of the cell, or the solution, is hypertonic. We know that the inside of the cell, we were given an osmolarity of 300, and this is 450, okay? So if that is the scenario, then we know that we are also hyperosmotic in our solution. So hyperosmotic and hypertonic. Great. Now, I have to let you know that this is not always the case where a question you might calculate that is both hyperosmotic and hypertonic. Sometimes you might have hypotonic but hyperosmotic, or vice versa, okay? And we'll take a practice of that in the next kind of question. Now, just to briefly clear up the units, okay? Milliosmoles per liter is going to measure the concentration of solutes in solution. Okay, and a good example of that is, for example, 200 milliosmoles of sodium ion. All right, millimoles is measuring the concentration of a compound in a solution, okay? Solution here and solution here, okay? And this would be, for example, 200 millimoles per liter of potassium chloride, okay? So that's the distinction there. Now, I want you to go ahead and try to do this question on your own, okay? I'll leave this drawing over here for you to kind of unpack, and pause the video right here and try to do it on your own, and I will go through the problem afterwards, okay? Alrighty, so hopefully, you paused the video and you did it by yourself, and if not, let's go through it together, okay? So this question says that a cell has an osmolarity of 300 milliosmoles per liter and is being placed in a solution of 150 millimoles of KCl and 50 milliosmoles of urea. What is the osmolarity on tonicity of the solution? Okay, so let's do the work here, okay? Now we know that, and let's change color here, we know that the value inside is 300 milliosmoles per liter, okay? We know that the solution has 150 millimoles of potassium chloride, which just means that it has, if I multiply by 2, okay, it has 300 milliosmoles, okay? 300 milliosmoles per liter of tonicity. Okay, so now we know the tonicity of the actual solution, milliosmoles per liter. Okay, and again, if you're confused, we just took 150 of potassium and 150 of chloride and we added them together. All right, 150 plus 150 gives us 300, or you can just multiply by 2 from the get-go. All right, so that is the tonicity. Okay, but what is the osmolarity? Well, osmolarity is both tonicity, is both non-penetrating and penetrating, and we know that our penetrating is 50 milliosmoles, so 50 plus 300 equals to 350 milliosmoles per liter. Okay, that is our osmolarity. So let's write that down. We have 350 osmolarity. We have 300 in tonicity. Okay. Now, we know that the tonicity inside of a cell is usually 300, so that means that there's no net movement of water going to be occurring. We know that the osmolarity of this cell is 300, and we know that the osmolarity outside is 350. Okay? Thus, the environment of the cell, of the solution, can be described as this. The environment is isotonic, but it is hyperosmolar. And is there going to be any movement of water in and out of the cell? Well, the net movement is zero, okay? Which means that the volume of the cell is not going to change. The cell is not going to shrink or expand. And the reason for that is that the tonicity is the exact same as inside, okay? And tonicity describes the non-penetrating solutes that actually generate that osmotic pressure. It doesn't matter if the osmolarity is high, because osmolarity takes into account both penetrating and non-penetrating, okay? But we only care about non-penetrating solutes when we discuss the movement of water, okay? Alrighty. So that is going to explain that. Now, guys, if this video has helped you understand what tonicity and osmolarity is, consider dropping a like, consider subscribing, and maybe watch another video of mine in this same playlist, okay? I thank you so much for watching the video, and I will catch you in the next one.